All right, so this is the continuation of Chapter 7. So here, as I was just talking about in the last video, we see the levels of carbon dioxide rising, and of course with that comes an increase in the average temperature across the planet Earth. All right, what are some possible consequences? So we're seeing, the melting of the polar caps, of course, which is causing the sea levels to rise. We're seeing more severe weather, and that's just going to get worse and worse. There's going to be large-scale crop failures, and then, of course, the deserts will get larger and larger. So, this is something we really need to do something about. Of course, tropical, because the whole planet starts to appear as though it was a giant. Just like the tropics, these tropical diseases will spread over larger and larger areas. All right. Anyhow, that's pretty negative stuff. So hopefully someday we'll do something. Someday people will do some things about that. All right. So anyhow, so how do we know about the interior of the Earth? We know that there's this liquid core that surrounds a solid core. How do we know those things? And the answer is seismic waves, sound waves. The way you can see an unborn baby inside of the mother using sound waves, ultrasonic. Anyhow, so here's how we've been doing this for many years. We have seismic detectors that detect earthquakes. So the earthquakes are produced all over the planet all the time, even ones that you can't really feel. And so there's actually two types of waves that are created during an earthquake. One is called a P wave, or a pressure wave, and one is an S wave, or a shear wave. And so the pressure wave, or the P wave, travels longitudinally. So that it just means that the thing that is waving is waving in the same direction that it's moving. And then the S waves are traveling. The wave itself is perpendicular to the direction that it's traveling. All right. So this is your classic sine wave. Anyhow, these waves behave differently in different types of materials. For example, the P waves can travel right through both solid and liquid. However, and this is the big key that allowed us to see, figure out what was going on inside of the Earth, the S waves, these waves, will only travel through solid material. All right, so take a look at this. So let's say you have somewhere on the planet there's an earthquake. Let's say right here is the earthquake, and we have these sensors all over the planet, all over. And by the way, we brought, when the astronauts went to the moon, they brought these seismic sensors to the moon as well. Of course, the moon is pretty much a dead world, and it hardly has any moonquakes at all. Anyhow, so what happens is, if on a line between where the earthquake took place and the sensor is, if it's just solid material, like over here or over here or over here, so there's just solid material between the earthquake and the sensor, then of course you're seeing both the S and the P waves. And the other thing, by the way, is of course, this is vast amounts of information. So we know that the S wave and the P wave right at this location came from this particular earthquake. And basically, we put all of this stuff into supercomputers and figure out, where these S and P waves came from. Anyhow, now take for example, on the opposite side of the planet, from where this earthquake is. Well, that the S and P waves would have had to travel through the outer core, which is liquid. We know that it's liquid. Why do we know it's liquid? Because the S waves can't pass through. The P waves pass through no problem, and the P waves, of course, we know how fast they travel, and so we can figure out what time they left that particular earthquake and how long it takes to get there. And so, again, we put all this information into supercomputers, and we can figure out exactly which part of the world that particular P wave came from. And so we can actually map the core, the outer core, and the inner core as well. How do we get the inner core? Notice these waves will actually bend, just like, for example, light will bend when it passes through glass, or when it passes through water, right? Light is a wave, and it'll do that, and so too do these waves. These waves will actually bend, and that bending we can actually measure it, and we can tell about we can tell what the size of the solid inner core is, and so forth. All right, so this is just a picture of some material right here. This greenish stuff is called olivine. Not that that's that important, but most of the rocks on the surface of the Earth are composed of combinations of oxygen and silicon, and together they're called silicates. Okay, so generally, if we were to break the rocks into their elements, what elements make up the rocks? We find that the rocks are 45.5% oxygen, 27% silicon, and then after that, as far as elements go, you get 8% aluminum roughly, and then roughly 6% iron, and that's actually really important. Where did this iron all come from? Of course, the iron should have, when the Earth was completely molten in the very early stages of Earth's formation, the heavier material ended up at the core. What is this iron doing at the surface of the Earth? And of course, we understand that. By the way, that has to do with the formation of the moon. So we'll get to that shortly. So anyhow, we also find calcium and magnesium, and then other, of course, other elements to a lesser extent. Okay, so this is, of course, the model for the interior of the Earth. So the crust, the mantle, the outer core, which is liquid, and then the inner solid core, which of course is so the core is just both cores are made of iron and nickel primarily. And of course, the density goes up as you get closer and closer to the center of the Earth. All right. All right. So this is just showing you that's the olivine. That's the stuff that the mantle is made of. All right. Yeah. Okay. I think we've covered all this. So the mantle, of course, is much less dense than the core. The mantle is rocky. The core, of course, is more metallic, mostly iron and nickel. The outer core is liquid. The inner core is solid. I think I've already covered all this. All right. Yeah, that's good. All right. So we again, when the Earth first formed 4.5 billion years ago, it was just a ball of molten rock, and the heavier stuff ended up at the center, the iron and nickel. Why is the interior of the Earth still hot? One reason, of course, is just simply gravity, right? That you have all this material crushing down on the center of the Earth. But the other reason that the interior of the Earth is hot compared to the surface is radioactive decay. We now know that there's a lot of uranium. Uranium-238 is one example, but there are other types of radioactive elements throughout the throughout the interior of the Earth, and that as radioactivity also emits heat, and so that actually turns out to be a really good thing, that the interior of the Earth is hot compared to its surface, because when the surface and the core of the Earth are at the same temperature, the Earth would be a dead world, right? Kind of like Mars, as a matter of fact. We think that the interior of Mars is much cooler than the interior of the Earth. All right. So anyhow, and by the way, that makes the Earth what's called an active world. All right. Using thermodynamic considerations, no one's actually measured this directly. The interior of the Earth, right at the core, is roughly 6,000 Celsius. About that's roughly roughly close to about 10,000 Fahrenheit. Just to let you know. So it's radioactive decay that keeps the interior of the Earth hot, as well as gravity, just by squeezing the Earth. The shape of the Earth actually holds in the heat a lot better than, like, for example, if the Earth were a giant cube. The cube would it has more surface area, and therefore it would lose energy a lot faster. All right, so how do we know the age of the Earth? I mean, how do we know the age of, the planet Mars or the Moon or anything? And that is through what's called radioactive dating. Now, let me explain it very briefly here. So basically what happens is you have certain substances that are what's called radioactive. What that means, when something's radioactive, it undergoes a change in its nucleus. And we can measure that. It basically changes either the number of protons, the number of neutrons, or it can even change. It's the number of protons and the number of neutrons. Although there is a type of radiation called beta radiation where electrons come out but they're actually coming out of the nucleus. They're not the orbital electrons that we associate with bonding. All right. Anyhow, so this is the basic idea. All right. So when you have a radioactive material, what we do in laboratories is we measure what's called its half-life. That is, when half of the material, you start out with, let's say, 1 gram of radioactive material. Over one half-life, you don't know which atoms are going to change, like that's the nature of radioactivity, but half of them will have changed into whatever they're going to become, whatever they're becoming. They change into other atoms. All right. So, for example, I'm simplifying this. It's a little more complicated than this, but let's take uranium-238. All right. We know that through experiments in the laboratory, we can measure the half-life of it. It's pretty easy to do. The half-life of uranium-238 is 4.5 billion years. And there are other radioactive half-lives, that start to approach the age of the Earth. Anyhow, let's say again, you start with 1 gram. If one half-life has occurred, then that 1 gram of uranium-238 becomes lead-206. After one half-life, half of that 1 gram that you had, half of it is still uranium-238, and half of it is lead-206. All right, so these are particular isotopes. Anyhow, you also have to have something that has a half-life of that is approaches the age at which you're going to measure. For example, you couldn't use carbon-14, which has a half-life in the thousands of years, to measure the age of the Earth. That would do you no good whatsoever. So anyhow, that's well, I'll take this up in the